Okay, so picture this. You're standing in front of a CNC lathe, new job lined up, and you're looking at that coolant tank.
Yep. Familiar scene.
And the questions start, right, do I really need to flood this thing with coolant? What about the mess and the cost and frankly the whole environmental side of it?
Mm-hmm. You probably just assume, yeah, coolant's part of the deal.
Exactly. It feels like a given. But what's really interesting and what we're diving into today is that, well, a lot of modern CNC turning doesn't actually use traditional flood coolant anymore.
That's the shift we're seeing. It's quite significant.
So the big question is, why? Why can so many turning jobs on these, advanced machines run without that constant coolant shower?
That's exactly what we want to unpack. We're going to use this great resource we have, the source material, to explore the reasons behind this move away from, well, constant coolant.
Okay.
And we'll figure out when coolant is still absolutely vital and look at some of the alternatives, too.
Right. Give you some solid takeaways to help optimize your own turning processes.
That's the plan. Give you some actionable knowledge.
All right, let's get into this paradigm shift then. Why are we seeing less coolant, sometimes none at all?
Well, probably the biggest driver is the huge leap in cutting tool technology.
The tools themselves.
Yeah, the materials they're made of, and especially the coatings, PVD, CVD coatings, they're incredibly advanced now.
Okay.
Some of these tools can handle much higher temperatures. And get this, some actually perform better when they run hot.
Wow, okay. That really flips the old thinking, doesn't it? A tool that likes heat.
It does. And then there's the cost factor. Cutting fluid isn't cheap.
No kidding.
Our source material points out it can be
Yeah.
16% of total manufacturing costs. Compare that to maybe 3–4% for the tools themselves.
16%, that's a lot. That's a big chunk of change just for the fluid.
It is. And then you add in the hassle and cost of disposal, environmental rules, worker safety concerns. It all adds up.
Right, the whole life cycle cost, not just buying it.
Exactly. Plus, something often overlooked is how much heat the chips carry away.
Yeah.
The source says up to 80% of the heat generated during cutting can actually leave with the chip.
80%. Just carried away by the swarf. That's amazing.
It's a very effective cooling mechanism, naturally. And then think about materials like, say, cast iron.
Right, it cuts differently, more powdery chips.
Yeah, it generates less heat to begin with. And going back to those advanced coatings, some of them, like thiolonin, actually form a harder protective oxide layer at higher temperatures.
So cooling them down is bad.
Well, flooding them with coolant can actually hinder that protective layer formation. So in those cases, coolant isn't just unnecessary, it might even hurt performance.
Huh. So better tools, understanding heat better, plus the cost and environmental stuff. It all points towards using less coolant where possible.
That's the trend. But, and this is really important, dry cutting isn't the answer for everything. There are definitely times when coolant is, well, non-negotiable.
Okay, so let's talk about that. When do you absolutely have to use coolant? When is it just critical for the job?
Well, think about the really tough materials. High hardness stuff, or materials that are just difficult to machine.
Like what?
Stainless steels, titanium alloys, nickel-based superalloys, hardened steels. Those generate tremendous heat.
Yeah, the kind of stuff that makes tools scream.
Exactly. Without coolant, the tool can literally burn up super fast.
Yeah.
And the workpiece itself can warp or distort because of the intense heat.
Okay, so extreme heat is a major reason.
Definitely. And also with materials that work hardened, like stainless steel.
Where cutting it makes it harder.
Precisely. Coolant helps keep that cutting zone temperature down, which sort of minimizes that hardening effect as you cut.
Gotcha. But you mentioned an exception.
Right. There's always a twist, isn't there? For some specific jobs, like hard-turning really hard steel with CBN inserts.
CBN, cubic boron nitride.
Yes. Those inserts often don't like coolant. It can cause thermal shock, basically cracking the insert because of the rapid temperature change. So it's very application-specific sometimes.
Interesting nuance. Okay, so tough materials. What else demands coolant?
If you're doing really long, continuous cuts or very deep roughing operations.
Just hogging out material for a long time.
Yeah. The heat just builds and builds relentlessly. Coolant is crucial there, not just for cooling, but also for flushing the chips out.
Right. You need to get those chips clear, especially in deep pockets or grooves.
Otherwise, they jam up, cause more heat, break the tool.
Huh.
It's a mess.
Okay. What about the final part quality? Finishing.
Absolutely critical there, too, especially if you need high dimensional accuracy.
Like for really tight tolerances.
Exactly. Think bearing seats, sealing surfaces, anything needing, say, IT6 tolerance or better. Coolant helps maintain thermal stability.
Meaning it stops the part from growing or shrinking with heat changes during the cut.
Precisely. It keeps everything at a more consistent temperature, preventing that thermal expansion that can ruin your precision.
Makes sense. Okay, what about sticky materials?
Ah, yes. The gummy ones,
Yeah.
like aluminum, copper, even some softer low-carbon steels.
They tend to stick to the tool edge.
Yeah, they form what's called a built-up edge, or BUE. It messes up the surface finish, increases cutting forces, and can even lead to the tool chipping or breaking.
Nightmare scenario.
Coolant acts as a lubricant in these cases. It reduces that friction and adhesion, preventing the BUE and keeping the cut clean.
Okay, lubrication is key there. Any other big ones?
Chip control, especially when you're turning long, slender parts or thin-walled components.
You get those long, stringy chips.
Yeah, they can wrap around the part or the tool, cause scratches, or just be a general hazard and pain to deal with.
So coolant helps break them.
Especially coolant delivered with some pressure. It can help break the chips into smaller, manageable pieces and flush them away effectively.
Right. So it really boils down to managing heat, providing lubrication, ensuring stability for accuracy, and controlling those chips.
That sums it up well. That table in the source material lays it out nicely. It's a good reminder that even as we talk about reducing coolant, it's still incredibly important in many, many scenarios.
Okay, so we know when it's essential, but the decision isn't just black and white based on material, is it? The way you actually cut matters too, right? The speeds and feeds.
Oh, absolutely. The cutting parameters speed, feed, depth of cut have a huge impact on heat generation and whether coolant is necessary or even beneficial.
I guess the basic idea is push harder, need more cooling.
Generally, yeah. Higher cutting speed, how fast the material surface moves past the tool, usually means higher temperatures.
Okay.
The source mentions CVG-coated tools, cutting steel, often work well with coolant in that 120, 250 meters per minute range.
But is it always just faster means flood it?
Not necessarily. There's a catch at very high speeds, particularly in some carbide tools. Flooding them with coolant can cause something called shock cooling.
Shock cooling sounds dramatic and bad.
It can be. The tool tip gets incredibly hot, then instantly quenched by the coolant. This rapid cycle can cause tiny thermal cracks in the carbide.
And that shortens tool life, obviously.
Significantly. So in those really high-speed scenarios, maybe just an air blast or perhaps a light mist might actually be better for the tool than a full flood.
Huh. So it's not just cooling, but the rate of cooling that matters. Fascinating. What about feed rate? Pushing the tool into the work faster?
Higher feed rate means you're removing more material per revolution. That increases the cutting forces and usually the heat.
Which means more wear, potentially worse finish.
It can, yes.
Yeah.
Coolant helps here by reducing friction and carrying away that extra heat, which generally helps tool life and accuracy.
But again, depends on the material.
Always. Like we said with cast iron, it produces those nice crumbly chips and doesn't get as hot, so you might get away with higher feeds without flood coolant. Steel? Probably not.
Okay, so feed is a balance between removal rate, heat, and friction.
Yeah.
And depth of cut, taking a bigger bite.
A deeper cut concentrates more force and heat onto a smaller section of the cutting edge.
So more stress on the tool tip.
Exactly. For those heavy roughing cuts, coolant is often really helpful to pull that concentrated heat away, protecting the tool and keeping the cut stable.
And for finishing passes, shallow cuts.
Conversely, yeah. If you're just taking a light finishing pass, you might not generate enough heat to need a flood of coolant if you have the right tool material and coating.
It really sounds like a complex equation. You're balancing productivity, how fast you can cut with tool life, the specific material you're cutting, and what the tool itself can handle.
It's definitely a balancing act. And speaking of tools, that brings us right back to tool material. It's absolutely crucial if you want to reduce or eliminate coolant.
Right. Makes perfect sense. If you take away the coolant's help, the tool itself has to be tough enough to handle the heat and friction. So what are the go-to materials for dry turning?
Well, modern tool materials are really what make dry turning feasible on a large scale. Cementing carbides are a good baseline.
Standard carbide inserts.
Yeah. They have good hardness, good wear resistance. They work well for many dry applications, especially, again, on things like cast iron that don't generate extreme heat. They can certainly take more heat than the old high-speed steel tools.
Okay, carbide is the workhorse. But for really pushing dry turning, you need more.
That's where coated tools come in. They are really the key enablers.
Those PVD and CVD coatings we mentioned?
Exactly. Things like titanium nitride, Tamahan, aluminum titanium nitride, all-tin, and other advanced multi-layer coatings. They're incredibly thin, but also incredibly hard.
What do they actually do?
They do a couple of things. They act as a thermal barrier, slowing down heat transfer into the tool's substrate. They also reduce friction between the tool, the chip, and the workpiece. And they massively increase wear resistance.
So like a heat shield and a low friction surface all in one.
Kind of, yeah. And what's really interesting, as we touched on before, is that some specific coatings, like TL,
The one that likes heat.
right, it actually forms a more protective aluminum oxide layer at higher temperatures. So for these tools, running them hot makes the coating work better.
Meaning flood coolant is actually bad for them.
It can be counterproductive, yeah.
Mm.
It cools the tool too much, prevents that optimal oxide layer from forming, and you might even risk thermal shock depending on the specific carbide grade and coating.
Mind blown again. So for some tools, you actively want them to run hot within limits. What about high-speed steel, HSS? Does it have any role in dry turning?
Less so these days for demanding jobs. HSS is tough, less brittle than carbide, and cheaper, but its heat resistance is much lower.
So maybe for very slow speeds or soft materials?
Perhaps. You might use it dry in those limited situations, but generally coated carbides are far more capable for serious dry turning.
Okay. So carbide, especially coated carbide, is king for dry turning. What about the really exotic stuff? CBN, PCD.
They definitely have their place. CBN cubic boron nitride is fantastic for hard turning machining, hardened steels dry.
Where coolant causes thermal shock.
Exactly. CBN thrives in that high heat environment. PCD, polycrystalline diamond, is more for non-ferrous materials like high silicon aluminum, but also often runs dry very effectively.
So the bottom line is, tool selection is absolutely critical if you're ditching the coolant.
Paramount. You gain the benefits of no messy coolant, no disposal costs, but you have to choose the right tool and run the right parameters to avoid just burning through inserts.
Makes sense. But what if you can't go completely dry, or maybe you just want to cut back significantly? Are there options other than just full flood or nothing?
Oh, absolutely. There's a whole range of middle ground solutions, often called near-dry machining or minimum quantity lubrication.
MQL, okay.
MQL, I've heard that term. What is it exactly?
Minimum quantity lubrication. It's a system that sprays a very, very small, precisely controlled amount of oil, usually mixed with compressed air, right at the cutting edge.
How small is
And we're talking milliliters per hour. Tiny amounts compared to the gallons per minute in a flood system.
Wow, so huge savings on fluid. Massive savings. And much less mist. Easier disposal. Often you can use biodegradable oils too, which is great for the environment and worker health.
And does it actually work? Does that tiny bit of oil do enough?
Surprisingly well in many applications. That targeted lubrication reduces friction right where it matters, which lowers cutting forces, reduces heat, and can significantly improve tool life compared to running completely dry.
So it's like a hyper-efficient lubrication delivery system. What about mist systems? Are they the same as MQL?
Similar concept, but often a bit less precise than true MQL. Mist systems generally use compressed air to atomize a small amount of oil, creating a mist around the cutting zone.
Still less fluid than a flood coolant.
Oh, much less. It provides some lubrication, and the airflow helps clear chips. It's cleaner than flood, generally lower equipment cost than full MQL, but maybe not quite as efficient with the oil usage.
Okay, another step down from flood. What about just air? Air blast.
Yep, simple compressed air.
Yeah.
Its main job is chip removal, blowing the chips away from the cut.
Does it cool much?
It provides some convective cooling, sure. Not as much as liquid, obviously, and zero lubrication.
So when would you use just air?
It's great for materials that cut easily dry, like cast iron, where chip evacuation is the main concern, or for materials where you absolutely cannot have any fluid contamination, like some plastics. It also avoids any risk of thermal shock.
Clean and simple for the right job. You also mentioned high-pressure coolant earlier. That sounds like the opposite of MQL.
It is, in terms of volume, but it's similar in being very targeted. High-pressure coolant systems use specialized pumps to deliver fluid at really high pressures, maybe 1,000 psi or even more.
Straight into the cut.
Right at the tool tip, often through the tool itself. The high pressure is incredibly effective at breaking tough, stringy chips and blasting them out of deep holes or pockets, especially in difficult materials like titanium or stainless.
So it's still using fluid, but using it much more strategically for chip control and cooling in tough spots. Requires special gear, though.
Yes, definitely needs pumps, filtration, and often special tool holders designed for high pressure through coolant.
Okay, so between MQL, mist, air blast, and high pressure, there's quite a toolbox of options beyond just on or off for the flood coolant pump.
Exactly. These near-dry or targeted methods let you find a sweet spot, significantly cutting down on coolant use while still getting the cooling, lubrication, or chip control needed for a specific application.
Well, this has been a really illuminating deep dive. It definitely feels like the days of assuming flood coolant is always necessary are, well, drying up in many cases.
Nice one. But yes, it's clear that while flood coolant absolutely still has its place for those really demanding jobs.
The tough materials, the heavy cuts, the high precision finishing.
Right. But for many other CNC turning operations, advances in tools, coatings, and these alternative techniques like MQL mean you can often run much leaner.
Leading to cost savings, less environmental impact, maybe even better efficiency in some cases.
Potentially, yes. It's about optimizing the whole process.
So for you, the listener, the real takeaway here is maybe to take a fresh look at your turning operations.
Definitely. Consider the specific materials you cut, the parameters you typically run, and the tools you're using.
Is flood coolant always the best answer? Or could you benefit from exploring dry cutting, MQL, or one of these other approaches?
It really prompts the question, doesn't it? Could you be saving money, simplifying cleanup, and maybe even improving performance by rethinking your coolant strategy? Something to definitely mull over next time you're setting up that lathe.